Chapter 11 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. Science and Hypothesis by Henri Poincaré. Chapter 11. The Calculus of Probabilities. No doubt the reader will be astonished to find reflections on the calculus of probabilities in such a volume as this. What has that calculus to do with physical science? The questions I shall raise, without however giving them a solution, are naturally raised by the philosopher who is examining the problems of physics. So far is this the case, that in the two preceding chapters I have several times used the words probability and chance. Predicted facts, as I said above, can only be probable. However solidly founded a prediction may appear to be, we are never absolutely certain that experiment will not prove it false, but the probability is often so great that practically it may be accepted. And a little farther on I added, see what a part the belief in simplicity plays in our generalizations. We have verified a simple law in a large number of particular cases, and we refuse to admit that this so often repeated coincidence is a mere effect of chance. Thus, in a multitude of circumstances, the physicist is often in the same position as the gambler who reckons up his chances. Every time that he reasons by induction, he more or less consciously requires the calculus of probabilities, and that is why I am obliged to open this chapter parenthetically, and to interrupt our discussion of method in the physical sciences in order to examine a little closer what this calculus is worth, and what dependence we may place upon it. The very name of the calculus of probabilities is a paradox. Probability as opposed to certainty is what one does not know, and how can we calculate the unknown? Yet many eminent scientists have devoted themselves to this calculus, and it cannot be denied that science has drawn therefrom no small advantage. How can we explain this apparent contradiction? Has probability been defined? Can it even be defined? And if it cannot, how can we venture to reason upon it? The definition, it will be said, is very simple. The probability of an event is the ratio of the number of cases favorable to the event to the total number of possible cases. A simple example will show how incomplete this definition is. I throw 2 dice. What is the probability that one of the two, at least, turns up a 6? Each can turn up in 6 different ways. The number of possible cases is 6 times 6 equals 36. The number of favorable cases is 11. The probability is 11/36. That is the correct solution. But why cannot we just as well proceed as follows? The points which turn up on the 2 dice forms 6 times 7 divided by 2 equal 21 different combinations. Among these combinations, 6 are favorable. The probability is 6/21. Now why is the first method of calculating the number of possible cases more legitimate than the second? In any case, it is not the definition that tells us. We are therefore bound to complete the definition by saying, to the total number of possible cases, provided the cases are equally probable. So we are compelled to define the probable by the probable. How can we know that 2 possible cases are equally probable? Will it be by a convention? If we insert at the beginning of every problem an explicit convention, well and good. We then have nothing to do but to apply the rules of arithmetic and algebra, and we complete our calculation, when our result cannot be called in question. But if we wish to make the slightest application of this result, we must prove that our convention is legitimate. And even then shall find ourselves in the presence of the very difficulty we thought we had avoided. It may be said that common sense is enough to show us the convention that should be adopted. Alas! Monsieur Bertrand has amused himself by discussing the following simple problem: what is the probability that a chord of a circle may be greater than the side of the inscribed equilateral triangle? The illustrious geometer successively adopted two conventions which seemed to be equally imperative in the eyes of common sense, and with one convention he finds 1/2, and with the other 1/3. The conclusion which seems to follow from this is that the calculus of probabilities is a useless science, that the obscure instinct which we call common sense, and to which we appeal for the legitimization of our conventions, must be distrusted. But to this conclusion we can no longer subscribe. We cannot do without that obscure instinct. Without it, science would be impossible, and without it we could neither discover nor apply a law. Have we any right, for instance, to enunciate Newton's law? No doubt numerous observations are in agreement with it, but is not that a simple fact of chance? And how do we know, besides, that this law, which has been true for so many generations, will not be untrue in the next? To this objection the only answer you can give is, it is very improbable. But grant the law. By means of it I can calculate the position of Jupiter in a year from now. Yet have I any right to say this? Who can tell if a gigantic mass of enormous velocity is not going to pass near the solar system and produce unforeseen perturbations? Here again the only answer is, it is very improbable. From this point of view all the sciences would only be unconscious applications of the calculus of probabilities. And if this calculus be condemned, then the whole of the sciences must also be condemned. I shall not dwell at length on scientific problems in which the intervention of the calculus of probabilities is more evident. In the forefront of these is the problem of interpolation, in which, knowing a certain number of values of a function, we try to discover the intermediary values. I may also mention the celebrated theory of errors of observation, to which I shall return later. The kinetic theory of gases, a well-known hypothesis wherein each gaseous molecule is supposed to describe an extremely complicated path, but in which, through the effect of great numbers, the mean phenomena which are all Eve observe obey the simple laws of Mariotte and Gay-Lussac. All these theories are based upon the laws of great numbers, and the calculus of probabilities would evidently involve them in its ruin. It is true that they have only a particular interest, and that, save as far as interpolation is concerned, they are sacrifices to which we might readily be resigned. But I have said above, it would not be these partial sacrifices that would be in question. It would be the legitimacy of the whole of science that would be challenged. I quite see that it might be said, we do not know, and yet we must act. As for action, we have not time to devote ourselves to an inquiry that will suffice to dispel our ignorance. Besides, such an inquiry would demand unlimited time. We must therefore make up our minds without knowing. This must be often done, whatever may happen, and we must follow the rules although we may have but little confidence in them. What I know is, not that such a thing is true, but that the best course for me is to act as if it were true. The calculus of probabilities, and therefore science itself, would be no longer of any practical value. Unfortunately, the difficulty does not thus disappear. A gambler wants to try a coup, and he asks my advice. If I give it him, I use the calculus of probabilities, but I shall not guarantee success. That is what I shall call subjective probability. In this case we might be content with the explanation of which I have just given a sketch. But assume that an observer is present at the play, that he knows of the coup, and that play goes on for a long time, and that he makes a summary of his notes. He will find that events have taken place in conformity with the laws of the